Hello from IIT Kanpur and welcome back. In the previous lecture, we discussed about vacuum technology, aspects of the various types of units that are used and various classifications of vacuum as well as the various types of pumps. Today, we will delve a little deeper into the science aspect of it. We will look at vacuum system analysis, and this is important if one wants to design a vacuum system or to make sure a process is going as per it is planned. So, let us see what we are going to discuss. First, the disclaimer. This is the outline of today's discussion. I will be briefly touching upon gas laws. These are topics you must have studied in your +2 or certainly in your undergraduation physics classes. Then I will talk about discussion about pressure and flow of gas molecules. Again, a lot of this draws upon what you might already know, but in the context of what we want to discuss, how to create vacuum or how pressure works. Then I will go into something which is directly linked to the vacuum technology, that is basic pumping equation, that is how do you what quantities do you relate, and interestingly this has a very similar analogy to Ohm's law, something similar you can use. So, this basic equation is useful to remember. Then I will touch upon how pipes have finite conductances, and this has bearing in how one designs vacuum systems. One should make sure that the pipe conductances are as high as possible, or to talk in the reciprocal space, the resistance should be as low as possible, so that we are able to pump down a system effectively. And finally, conclude with modeling the rate of pumping in a real situation, and we will see how the pumping happens and how the pressure falls and what are the practical limits of how low a vacuum one can get. So, we start with the gas laws. All of you might remember Avogadro number. In fact, these are amazing concepts where the concept of molecule was introduced, and where it was told that a fixed volume of any gas under standard temperature and pressure would have a fixed number of molecules, which was evaluated to be approximately 6.022 10 to the power 23 molecules, and this is what you call 1 mole, right. Now, 1 liter is actually 10 to the power -3 cubic meter. So, now it turns out that this particular unit was started off at a time when SI units and all were not so well established, right. It got established much later, which is why we have the unit liter, but it does not matter. We know what the conversion numbers are. And what is STP, that is standard temperature and pressure? They have taken it as 273 Kelvin. 273 Kelvin happens to be 0 degree centigrade, typical melting point of ice, and 1 atmosphere. Now, when we look at it very closely, of course, one may question what is 1 atmosphere and what is melting point of ice, because it varies according to the pressure and other conditions. But that being said, we have already seen 1 atmospheric pressure is 760 millimeter of mercury column, right, and 273 is a standard that is taken for the melting of ice. Now, the m is the mass of the molecule, and note that in air there is oxygen and nitrogen, 78% nitrogen, 21% oxygen. This is what helps us breathe and survive. Then we have, in fact, nitrogen also plays an important role for our survival, and then we have the traces of argon and carbon dioxide and so on. Now, on an average, you can assume that for practical purposes, for your design of vacuum systems, the molecule in air, regular air, ambient air, has a molecular weight of 28.85, which is a weighted average of these, and it can be it's usually expressed in atomic mass units, and so you can convert it into grams, because 1 mole will be the atomic weight or molecular weight equivalent in gram. So, this m turns out to be this 4.79 10 to the -23 gram. This is the typical weight of an air molecule. So, in kilogram it will be this, okay, because SI units is MKS, right, meter kilogram second. So 10 to the minus 26 kilogram. This is for air. So it's good to remember these numbers. We have studied this in our undergraduation classes and we have studied in our 12th, but we will be using these numbers for various calculations that may come up in your assignment. And also of course in the practical design in the lab or in the shop floor. Now what is ideal gas law? Ideal gas law is PV is equal to NKT. N is the number of molecules per unit volume, and then you have a number of molecules. P is the pressure, V is the volume, K is the Boltzmann's constant, which turns out to be 1.38 10 to the minus 23 joule per molecule per Kelvin, right? And T is the absolute temperature in Kelvin. At 300 Kelvin, these are the numbers. Now, torr liter is, as I said, it's a common unit, especially in many American settings and many American companies. But SI units is what many people use. You may use this. Another popular unit among scientists is electron volt, because when you talk of energies, you want to make sure that it doesn't become some unwieldy number with exponents and all. So when you divide by the electronic charge, then you end up getting expressing the energy in electron volt. So these are some useful numbers to remember, and often if you ask in any situation, you can always get these. And today, of course, with the internet, these are very easy to get. But all the same, you need to know how they come. So this is the important thing. PV is equal to NKT. Pressure times volume is equal to number of molecules times K times T. Okay. Now we go to some novel concepts. One of the things to note is its ideal gas law. That means it's assumed that the molecules that are going around, they are not interacting with each other. And usually the ideal gas law becomes more and more accurate at very high temperatures and very low pressures, because the molecules will be moving very fast and very little interaction, and very low pressure means it's very sparse. So that is where these laws are typically valid, and first order in our normal ambient also you can use these with some errors that will come because of the molecular interactions that may happen. Now there was an interesting law proposed by Dalton, and it's famous as Dalton's law of partial pressures. So what he's telling is the total pressure that you find in a chamber would be equal to the partial pressures exerted by the individual molecules that occupy that chamber. So this is very interesting because it orthogonalizes the whole process, right? So if there is oxygen which is applying pressure versus hydrogen versus nitrogen versus carbon dioxide, whatever, so they are all independent. They independently apply pressure on the walls. They don't even know the existence of the other things, and the total pressure that will observe is the sum of the pressures. What is pressure? Pressure is the force exerted by molecules bombarding on the walls of a container, right? So that's what it would be. So, and then of course N total will end up being N1 plus N2 plus N3 and so on. And using ideal gas law, you can see that P1V, V is the same for all because it's in the same chamber and the molecule can move anywhere in the chamber. So P1V is equal to N1 KT, P2V is equal to N2 and so on. So this is a useful thing to know, and this Dalton's law of partial pressure allows us to work with a lot of situations, especially when you are doing semiconductor processing. Sometimes you may be introducing another gas. So to know how many of those gas molecules are going to bombard on the surface or on the walls of the chamber and so on, wherever you are wanting to study, this partial pressure law helps us to evaluate it more reasonably accurately. In fact, it's quite accurate, and that's one reason when you go to very low vacuum, these ideal gas laws become very low pressures, that is very high vacuums and very low pressures, this ideal gas laws becomes more useful and more accurate. So clearly you can use these ideas in order to get what is the role of each molecule in a mixture of gases. We also need to know some other quantities, and I'll touch upon some of them. One of the topics you must have studied is what is the average velocity of a molecule in air, right? In a gas. So one of the ways to do that is you should know the temperature, and from Maxwell's Boltzmann distribution, you can know that if you take a weighted average, that is what is the velocity and what fraction of the molecules are going to be having that velocity, and you can do a weighted average, and it turns out to be square root of 8 kT by pi m. This is derived purely from basic physics, and I am sure many of you might have worked it out also in your undergraduation. And but this is a useful number to keep in mind. So average, the actual average that we talk, arithmetic mean, weighted average, would be this, and that ends up becoming 469.14 meters per second at 300 Kelvin. I want you to look at this number because it's a very important number. So this is where so you can see how fast it is, first of all, and this is what is you find is the speed of molecules in air, and that's why when you go to supersonic speeds, you are actually going faster than what the molecules are going. An average molecule is going. Of course, some molecules can be going fast, some molecules will be slow, but average molecule is this. So this is average velocity that you have. But note, when you say average, average is a much misunderstood term. Average is just some number which sort of represents what is happening in the system. So there are various averages you must have studied: geometric mean, harmonic mean. You must have also studied median and mode. All these are expressions of some number that represents what's happening in the whole population, correct? So clearly you have to choose the appropriate average according to the condition and what you are doing. So if you look at it, there are two other popular average velocities that often come up. One would be, depending on the context you have to use it, if you look at the kinetic energy of the molecules and work it out, this is very easy to work out because equipartition of energy says every degree of freedom as half kT, so you can actually work out. So 3 degrees of freedom, you will end up getting average RMS velocity would be square root of 3 kT by m. Okay, and you can, and similarly there is another number, the Boltzmann distribution we have. So the velocity will be distributed. So what is the most popular or most likely thing that you are expected to encounter? So the peak of that velocity distribution Boltzmann is what will tell you. So that ends up becoming square root of 2 kT by m. Okay, these numbers, while are pretty close to each other, but they represent, you use them according to the situation of what you want to do and according to the problem at hand. So I would encourage you to work out the numbers for these at room temperature. Already the value of Boltzmann constant and the average mass of a molecule in air has already been given to you. So it will be a good thing to work out and see what the values are and appreciate for yourself what's the difference in the three, how much different are they. So that's about velocities. That's important because it will tell us how agitated a molecule is at a given temperature, and if you want to find out the average agitation, you use the average velocity and so on. Now comes another important thing, the mean free path. This mean free path is a very important concept, especially when you are talking of vacuum, because you want to know whether, say you are evaporating some metal and it is going up and there is a substrate on which it's supposed to get deposited. So if as it is evaporating, you want to make sure that only the metal goes and hits the surface, because there are lots of gas air molecules that are going around, right? But the, say, aluminum that you are evaporating, you don't want it to interact with the air molecules and then go there. First of all, it will slow them down, and secondly, you may find that some contamination will also come in. Some other gases, oxygen, water vapor, other things could also come into the deposition that you are doing. So what is the way out? You go to low pressures or high vacuums and you do the evaporation. So in this case, how low a vacuum should you go and how big should be the chamber and so on, these things are found out by knowing what is a mean free path. What is the distance a molecule is likely to travel before it collides with something at the given pressure and temperature. Okay, so that is something that you may want to know. So mean free path, here we are just plucking out those formulas, and these can be derived very nicely from first principles. There are assumptions there, and that's why it's good to know how the assumptions are, so that you're not caught off guard by choosing something when it's not valid. But anyway, lambda is the mean free path. That is equal to 1 over square root pi d naught square times n. So what are these values? The small n is number of molecules divided by the volume. So it is number density, right? Number of molecules per unit volume. And D naught, as in many situations you will find in, especially in engineering, you'll always find some fitting parameter that sort of captures what's happening, because you don't know exactly what the physics is always, or you don't want to go into the deep physics of what is happening sometimes. So you choose a number D naught, which is the molecular diameter. This is not very precisely known, or rather it's not defined precisely. It can be different situations. People who are conservative may take a value, who are optimistic may take some other value, and so on. So, but typically this is 3.5 to 4 angstrom. This is in a way telling you what is the distance over which there is interaction between the molecule and something else that is around it. So this is one number. So you can choose any one of them, maybe for rounded number if you can choose, if you want to do mental calculation 4, but otherwise 3.5, but around this number, okay. And you should be aware that you are making this assumption. This gives you the value for lambda, and that gives you the order of magnitude, because that's what we are most interested in engineering many times, not exactly not the exact number of some intermediate quantity, but the order of magnitude, so that the final quantity we know very precisely. So for air at 300 Kelvin, you can actually evaluate these, and usually it is expressed with some standard empirical formulas. So it is based on this, you can plug in the numbers. It works out to be, because N is actually dependent on the pressure, right? PV is equal to NKT, we know that, right? So you can replace that, and it turns out to be 6.67 divided by P when it is expressed in Pascal. Pascal is your SI unit, and or it is 0.05 divided by P in torr, which is a practical unit. Or if you want to look at it another way, the mean free path in 1 atmosphere. 1 atmosphere refers to atmospheric pressure, the normal pressure that you have in a lab or in the ambient, right? So for normal pressure, it will be 65.8 nanometer is the value of lambda. So on an average, a molecule is likely to travel 65.8 nanometer distance without colliding. You can look at it two ways. The molecule size typically is of the order of half a nanometer to 1 nanometer or so, right? Or usually much lower than 1 nanometer. So half a nanometer you can take. Hydrogen atom, you know, is 0.5 angstrom. So typically that's the order. So clearly it travels many times its size before it collides. So in a way, what we are assuming that it's not interacting with something else around is not very unreasonable. But if you look at it in another way, if you look at the distances that we deal with in our real physical world, normal physical world, you find that 65.8 nanometer is actually really small, right? So human hair is about 100 micron, right? So actually it's actually much smaller. So but then notice that if you talk of modern electronics, these numbers are the sizes which we are dealing with, transistor channel length and so on. This is why we need to know all this a little bit more precisely and more accurately, and this is where the challenge comes in, because statistics has to be valid. It is not just about statistics can be automatically taken for granted. When you are reaching the values which are close to the average sizes, you have to be careful that there will be some more errors will start coming in. On the other hand, if you are at distances much larger than 100 nanometers, for example, if you are using 1 micron or even 1 millimeter, it's as though the molecule collides many times. Okay, so depending on the context, this is small or large, but this is an interesting number you may want to keep in mind as general knowledge at 1 atmosphere. Now, the question comes, what if I want to design a chamber which is 30 centimeter high, and the pressure we go is this? Okay, so now the question is, what fraction of the molecules will interact with some other molecule before it reaches the substrate? And remember, when you want a pure deposition, you want very small fraction of the molecules interacting with something before it reaches the substrate. Otherwise, there's contamination, right? You don't want the contamination to be more than the actual thing. Supposing I want to buy rice, I don't mind once in a while some pebble here, there, not you can pick it out and put it away. But if more of the rice is mostly pebble, then it's not rice, right? You cannot, it's not fair. So same thing here, as the molecule is going up and it's trying to deposit on something, you want to make sure that it hardly interacts. So this can be found out using this lambda value. You can evaluate for this pressure and it will tell you what fraction is likely to collide. So and this is one of the reasons you choose a low pressure for depositions, okay. And this is where we saw the classification of deposition. Depending on what you are doing, CVD, some amount of collisions is okay. Thermal deposition, you want lesser collision. Molecular beam epitaxy, you hardly want any collision, okay. So you can see that's why the pressure keeps dropping as you do those processes. So I would request you to evaluate this and try this out as well. So that's about the mean free path, okay. But there's another important thing that we often need to encounter. If I have a chamber where some processing is going on, what fraction of the molecules are hitting the chamber of the wall of the chamber, right? What fraction? So, and also if there are corrosive gases, you want to make sure that numbers, before it reaches pitches on the wall, it's pumped out. So these are things that you have to design sometimes, or you have to make sure it doesn't reach the place, or sometimes you want it to reach the place. You want to have sufficient number of bombardments so that your process happens as you want. So the other parameter that often people talk about is impingement, or the flux of molecules that are hitting the surface, and phi can be defined as n times average velocity divided by 4, the number of molecules striking unit surface per unit time, okay. This is a very useful number to know what will be the contamination you will have if you put something and expose it to environment. This is one of the reasons we have clean rooms. We don't want to bring it out in the clean room and take it back into the chamber, because we may think I just brought it out for 1 second or 2 seconds, but look at it. At maybe atmospheric pressure, you can see a huge number of bombardments are taking place. So if you look at a number at 300 Kelvin, phi ends up becoming 3.76 10 to the power 20 times P, okay. And that in 1 atmosphere becomes 2.86 and 10 to the power 23 centimeters per centimeter square per second. So this large number of molecules are actually bombarding per the surface. So if you bring a wafer to the atmosphere, within 1 second these many molecules are bombarding, okay. Of course, you may say that there are a lot more molecules, but still depends on the contamination level you are handling. We remember that we are talking sometimes about parts per million and parts per billion type of purity. So you want to make sure that that doesn't happen. So what do? You don't bring it to an ambient environment with molecules that are not acceptable. You make sure it is in vacuum. And again, there is a similar calculation for 10 to the minus 6 torr. This is the pressure at which you do the thermal evaporation. You find that 3.76 10 to the power 14 is the number of molecules that are bombarding. Still large. Actually, this is nearly equal to the number of molecules present on the surface density. If you look at it, is that order of magnitude. So that means even at 10 to the minus 6 torr, the surface density of molecules are bombarding, okay. So you have to, of course, you have to play it out and check it out empirically, what affects your process, what doesn't affect your process. It all depends on that, okay. So this is how you find out what is the surface bombardment that is taking place. But then there is another parameter which we all are familiar, and we have talked about it already: pressure. The pressure can be evaluated as P is equal to N times the molecular mass times velocity, average velocity square divided by 3, okay. So this is what it is for the pressure. You can evaluate this also, and if you know some of the numbers, you can evaluate the others. So interestingly, the physical world is such that all these parameters are all linked to each other, and in a way the fascinating thing about modern science is being able to precisely evaluate all this. So it's just about being aware, and once you are able to evaluate all this, you know what parameter to control and what to not to be worried too much about, in order to make sure that you are able to do what you want to get done. So that is the interesting thing, and that's what we will do in IC fabrication as well. So that was about some basics of the basic physics review, and let me also talk about some parameters and some terms that you are likely to come across as you are doing some semiconductor processing, whether in your lab for your experiments or if you are working in some company, depending on what type of task you are doing. So let me talk about a few parameters. Interaction with walls. First of all, when in thermodynamic equilibrium, it's important to remember that the condensed phase and the vapor phase are in equilibrium. Okay, so you have to, sometimes you work in thermal equilibrium, sometimes you move away from thermal equilibrium to make sure what you want happens. Say you want more of vapor, so you make sure you, before thermodynamic equilibrium happens, you remove the vapor. Okay, so that so otherwise it will condense, or you choose a material where the vapor pressure is very low. Okay, then vapors and gas, there is a difference. Gas is something which is in our normal interaction, it is actually in the gaseous state. Vapor is something in a normal interaction could be in the liquid state, and that's getting converted into vapor. That's why you say water vapor, because typically we are used to seeing water, but water vapor also exists even at room temperature. Only thing, most of it is water. When the equilibrium is such that it tends to condense more than evaporate or be in the vapor state. So please note the difference between these two. You must have studied these in school, but it's important to review those. Then there is vapor pressure. So this is the equilibrium pressure for when there is no change that is happening between the, so at what pressure will the liquid and the vapor be in equilibrium. Okay. Then absorption. Absorption is something that happens in the volume of the material. Okay, absorption is something that happens in the volume of the material, but typically in vacuum systems we talk about adsorption. The B becomes a D, right? Adsorption, which is something that is absorbed at the surface. Okay, so and typically adsorbate is something that is getting absorbed. Then physisorption is the method by which there is no chemical interaction. If you heat it up, maybe it will just come off. It is physically in a lower potential state, and that's why it's physisorption. Chemisorption is where the chemical bonds are starting to form. So to remove it, you will have to do something more. You might have to bombard with much higher energies if you want, with other gas molecules to remove those, or do some chemical reaction. Surface migration is something that can happen because when molecules bombard on the surface of a chamber, they can get adsorbed, and once they are adsorbed, they can move on the surface. This is the surface migration. They can diffuse. Desorption is how do you remove these adsorbed materials, and this is important. Why? Because if we don't remove the material, what you may find is over time they slowly degas. So desorption is sometimes a good way to ensure there is nothing there. Okay, so desorption, how do you do? By applying higher temperature. Thermal energy could be done so that these molecules start, higher temperature means average molecule starts vibrating faster, and the chances are that it will come out of the potential well and come out of the surface. Photo energy can be given, energy of impact of ions or electrons. These are some of the tricks people use for desorption of the from the walls of the chamber or from the substrate, whatever, depending on what you are trying to do. A few more terms. Vaporization, the generic term. Evaporation, it's volume, and the volume based. Evaporation is from the surface. Okay, so deep down the chance of that molecule becoming a vapor is very less. On the surface it's evaporating. Sublimation, from solid to gas directly. Certain materials do that, iodine for example, and various things. Even in fact, all materials all the time do that. For example, even ice could sublimate, right? You can find some vapors coming out of ice. Now, but then some rates are higher, some rates are lower. That's what we are talking about. Then outgassing. Outgassing is, we saw adsorption, right? Outgassing is slowly things will come out of the chamber. So you will have a chamber, you may think it is clean, there are nothing there. So, but then with time, slowly some gas molecules or vapors will start coming. A good example of that is water vapor. If you find that in even some places where the walls are damp, you may find that your clothes are not drying because the walls are actually releasing the molecules time, slowly, right? Same thing could happen in the chamber. You will find that you are trying to pump down, but you are not able to pump down to low pressures. Why? There is desorption, and the desorption, and which is the outgassing of the water vapor from the walls. So what do you do in such cases? Where as we saw, desorption is encouraged. You could heat up the wall of the chamber. These are some practical things that you should know. If you find that the vacuum is not coming because and you keep having to pump down, and the likelihood is the chamber was exposed to the environment. When it's exposed to the environment, water molecules can get adsorbed on the surface, and especially in a humid environment, that's even more so. Now when you start pumping down, the air inside and the gases inside, they may get pumped down, but slowly the walls will start desorbing. Why? Because the vapor pressure is there, and so there will be a tendency for it to vaporize more, and so you'll find that the actual pressure doesn't go down. One of the ways is to heat up the wall of the chamber, and we saw some other things like applying that with light photons. You can excite them and remove them, or depending on what you are trying to desorb, you could also use ions. In fact, argon and ions are often used to bombard. Argon is inert, it's an inert gas, right? So it doesn't usually affect the other properties, chemical properties. So you use argon to bombard the walls, and then when they bombard the walls, they remove the moisture, and once it's moved, it of course can be pumped out. Okay, so outgassing is a very important challenge that you may find, and this can be because of vaporization, thermal desorption, then diffusion, and from some place where it's available to it comes up and then desorbs, permeation of the outer chamber, then electron and ion stimulated desorption. So various types of outgassing can happen. Okay, and one has to learn them very carefully depending on what system one is working with. Impinge rate we already saw, that will be 3.5 into this. This is an empirical way of evaluating it. Sticking coefficient. Many times we may want to model what is the number of molecules that are going to stick on the surface. For example, you are wanting to make a monolayer of a compound semiconductor. Gas molecules are coming and staying there. You want to make sure that if 100 of them are there, what fraction remain? So this is the sticking coefficient. So that is there, and then monolayer time is the time it takes for one monolayer number of molecules to fall on the surface. So now this is important, especially nowadays because we are trying to epitaxially grow stuff. So when you are epitaxially growing, you want to make sure only the known material is getting deposited, and that's what is growing. Silicon germanium, if you want, silicon germanium in right proportion should come and should get deposited, so that you get the right band gap and right stress and so on, stress in the crystal that is grown. So these are important parameters, and you will keep coming across later as you go for more advanced processing. Then now we shift gears. These are things again you may be familiar, but in the context of vacuum technology. One of the useful things to know is gas flow rate. One popular unit is SCCM, that stands for standard cubic centimeters per minute. Notice that this is not SI unit, this is a very practical unit, and many gas flow meters are usually sold with SCCM ratings. And not just that, this can be controlled very well with modern technology, and this is why we are able to do epitaxy, because you are able to precisely send that many number of molecules. So this is what is standard here. Standard cubic centimeter means at 0 degrees and 760 torr, the equivalent number of molecules that are there, that is flowing per minute. Okay, so that is what it is telling. So the actual temperature at which you are operating can be different, but you have to work backwards using the equations that we know. So typically it is 2.69 10 to the power 19 molecules per minute at atmospheric pressure and 0 degree centigrade. Okay, so this is the number of molecules for one SCCM, and this will tell you, supposing you need to deposit 10 to the power 14. So you know, in a fraction of a minute you are able to deposit all these, the right number of molecules. Then we come to another parameter that we use in vacuum technology, pumping speed. Pumping speed, please be careful, because it is actually the volume of a specific gas. passing through a plane per unit time. This can change because depending on the pressure, depending on the temperature, these things can change, right? So, but for a given temperature and pressure, the volume of a specific gas that is passing a plane per unit time. So, this units are typically cubic centimeters per second or liters per second. Okay. So, this is so pumping speed, when I say, I am talking of the volume of gas, but this is actually not so precisely known, right? Because as I said, it could depend on the pressure and this thing. So, there is another parameter that we may go to, and then but then pumping speed is something you can measure, right? So, another parameter that you use is the throughput. This is the actual mass of molecules, the actual number of molecules that are removed per second. So, if I want to pump down a chamber, this is what I have to find out how many molecules I need to remove, and how many are at that particular instant, how many molecules are removed per unit time is the throughput, or Q. Its unit is Pascal per meter cube per second. Actually, if you analyze this, it turns out to be the unit of energy. Okay, it's interesting to see this. So, it's 1 watt. Okay, and another practical unit, especially American units, is torr liter per second. Now comes the most important equation that we need to remember. This Q that we have is linked to S by this equation. Q is equal to S times P. Of course, there is a caveat which I will be coming in the next line, at a given temperature. So, Q is equal to S times P. Now, what is S? S is volume per unit second. So, it is essentially P dV dt, where P is the pressure. Now, Q is used instead of Q by kT, because this is a practical thing that you will find, but you have to make sure that is the case only if it is at a given constant temperature. It is only an isothermal system, right? So, many times we assume that it is the room temperature and that does not change because of the pumping. It could change, maybe some part is getting heated by something. Okay, you should be careful about that. But first order, you can design things without having to worry about it. So, Q is equal to SP for a given room temperature. Strictly, it should be Q divided by kT. Okay, this is comes from gas laws, right? N per second, number of molecules per second. So, if you look at the relationship, it will come to be Q by kT is what is constant. So, the power, another way of looking at it is power flow rate is equal to mass flow rate, right? PdV, we remember, is work. You might have studied it in your mechanics and so on. So, power flow rate is equal to mass flow rate, but this is true only if the system is in isothermal. Okay, the T is considered to be constant, then you can treat these to be equal, and then you can use that for your calculation. But the most important equation I want you to remember and take away from this discussion should be Q is equal to S times P. Q is the throughput, that is the number of molecules removed per second. S is the volume per second. P is the pressure. Now, if you remember this, and that is why the title of this slide itself is Q is equal to S times P, you can work it out. So, if you look at it, the molecules that are going out, say this is the chamber and the molecules are being pumped out. One thing is conserved. As in many other situations, you will find what is the quantity that is conserved, right? Typically, you want to make sure charge is conserved. That is why you have the Kirchhoff's current law, or potential is conserved, and so on. Energy is conserved. In this case, the number of molecules is conserved. You are assuming that nothing happens, no breaking of molecules, those things are not happening. Molecule is conserved, number of molecules that are removed per second. So, from the chamber to the pump, that thing is continuously constant. So, Q is equal to kT dN dt is constant for isothermic system in steady state of pumping across any plane. Now, using that relationship, you can see that at any location, if the pressure is P1 here and the pumping speed is S1, so P1 S1 is equal to P2 S2 is equal to P2 S3 is equal to so on, is equal to whatever is coming out, right. So, this is the important thing here. So, P1 S1 is equal to P2 S2. So, this is what you use to evaluate what should be the pressure at a particular point and what is the pumping speed. So, pressure sometimes you can measure, So you can estimate what is the pumping speed. Okay, so you use given pressure and pumping speed at a particular place, you find out what Q is, use it in a place where it is supposed to be conserved, and you can get the equivalent Pn and Sn. Now that being said, it is important that the pump is pumping out, but looks like as it is going down, closer to the pump, it is pumping very fast, lot of volume is coming out, but further away from the pump, maybe the pumping speed is low. So why is that happening? That actually can be modeled as the conductance of the pipe. This is very critical to note. So this conductance of the pipe C is equal to the throughput divided by the drop in pressure. C is equal, this is defined this way, C is equal to Q divided by delta P. So instead of calling it S times P at a particular place, you can talk of the difference of pressure at two places, and you can throughput divided by difference of pressure is the conductance. So this is very similar to your electrical equivalent, where you have current I divided by the voltage will give you conductance in the electrical world, right? So here also the same thing, and its units are cubic meter per second. So this is a useful thing to note. So this actually has the same unit as the pumping speed, remember that, okay. So parallel connection, so if I have lots of parallel connections, and you can see that when the parallel connections, Q's will add up. So you find that C is equal to C1 plus C2 plus C3 and Cn. But very often more than parallel connections, you have serial connections, right? So what is happening is you have one pipe, then you can connect another pipe, and so what ends up happening is it's a serial connection. So overall conductance that you will have will be the sum reciprocal of the sum of the reciprocals. This is similar to resistances put in series. Reciprocal of conductance is resistance, right? So you can look at it that way. Now this is an important concept, because if you look at it, chamber outlet pressure here is equal to the pumping speed minus reciprocal of pumping speed minus the reciprocal of the conductance. So what it means is, whatever huge pump you may put, there will be always some drop in the pumping speed by the time you reach the chamber because of the long pipe. So this is extremely important concept, and you will find that in some cases you can never reach a particular pumping speed for a given at the chamber for a given this thing, because there will always be some conductance unless you are able to remove it and directly put it there. So what is it from a practical point of view? Whenever you are working with a vacuum chamber, do not put long pipes. That's a practical takeaway, I would say. Mathematically you can show that. Do not put long pipes if you want to pump down something. Bring the pump as close to the chamber as possible. And this is why, if you remember in the previous discussion, the high vacuum pumps used to have a huge openings so that they are able to pump down with very little conductance between them and the actual pumping area. So that is very critical for this. So I want you to remember this as a useful thing. So by changing the tube impedance, one may increase the pressure in the chamber, and this is called throttling. So there is another thing that people do. Supposing I want to quickly increase the pressure in the chamber and there is a pumping going on, what I can do is I can narrow this pipe. If I narrow this pipe, you can see that the conductance will decrease, so this pressure here will go up. This is a useful trick during processing. Many times when you are doing reactive ion etching and all that, sometimes you want anisotropic etching, sometimes you want isotropic etching. If you want to switch between those, you want to change the pressure inside the chamber. So one way to do that is, if you want to suddenly increase the pressure, throttle it, that is narrow down the pipe, right? And if you want to lower the pressure, sometimes you want to increase the conductance. So you release the throttle. So let us now look at see how actual chamber gets pumped down. This is important. So supposing this is the chamber and you have a pump and there is a tube that is connecting it. As I said, you should make this as small as possible, but here, for example, let us take there is a tube that is there. Now if you look at it, the pump is pumping out, right? But what is coming from this side? Of course, the material from inside the chamber that was already existing. But in real life, there are more things. It's not just that. You'll find that some gas leaks will be there on the chamber. So that is QL This is the throughput of gases that are molecules that are going in per second through some leak. Then you have this notorious thing of outgassing, right? So the gases that are absorbed in the walls, they start desorbing as the pressure decreases, and that will become more a significant component of what is present in the chamber then. And only problem is, since the gases that are absorbed here have very high densities, they can keep desorbing over many hours or days depending on what it is. So that's where you have to take action. But of course, if you take action, this can be brought down. Then there is also another point, that while it is true that you are pumping down and all that, we have seen that we are dealing with very low pressures, right? So many times it may be that some molecule here never collides because of the low pressure and can go back into the chamber, or something, the desorption in the walls of the tube also can go back. So this is known as the backflow part of the pumping. So now we can express this by a simple differential equation. Minus V times dP, this is the amount of work done, right? So this is minus because it is decreasing over time, right? You are removing material from the chamber, is equal to dt, the time over which it is done, times S times P, right? S times P is Q, right? For the particular pump. But there is also, this is taking it in this way, but there are 3 Qs out here which are feeding from the other direction. So the total SP that is removed minus QW minus QL minus QF. Okay. Now we can write this as a proper differential equation. We can bring the dt here. So minus V dP dt is equal to SP this. This is the first order differential equation. All of you are very familiar with these equations. So at equilibrium, what do you have? dP dt will be 0. If dP dt is equal to 0, you have no change happening over time. That is, whatever is pumped out, something is pumping in. So what do you find in that situation? You find that the pressure, this becomes 0, then the P becomes Pu. So P ultimate times S is equal to QW plus NQL plus NQF. Okay, this is a very important parameter that you should remember. Why? Just because you have low final pressure, it does not mean that you have good vacuum or a contamination free environment. It can be that Pu is small, but you have put a huge monster of a pump that is just pumping out fast. So it gives you a feeling as though the pressure is low. But in reality, from outside, gases are coming in. This is something that you have to be wary about. So that's why just because the pressure is low doesn't mean it's contamination free. Pressure should be low and there should be no leakage paths from elsewhere. So sometimes putting a pump with lesser capacity and pumping over a long time is safer to ensure that there is a cleaner environment. Of course, it's a trade-off between the time that you take to pump down and all that. So people often want to go for a heavy pump, but whatever you do, make sure that these things are as small as possible. So this should be QW plus QL plus QF. So effective pumping speed will be, the actual effective pumping speed that you may end up having, you can define it as SE times P is equal to SP minus sigma Q, and this can be written as, because sigma Q is this, so you can write that as S equal to P minus P ultimate. So so SE becomes the pumping speed of the pump multiplied by 1 minus Pu by P. So this is just mathematical jugglery, but these are useful expressions that can be used. So the effective pumping speed is 0 when P is equal to Pu, right? Because when the P is equal to Pu, when you reach the ultimate pressure, the effective pump, no more pumping is happening. Effective pumping is, your pump is pumping, but how much are you actually taking out? That is effective pumping. And once you have reached the ultimate pressure, whatever is coming in, you are taking out. So net no change. So no more pumping action is as such happening. Effectively, nothing is happening. Of course, a dynamic equilibrium, but watch out. So this is a useful thing to remember. So one key parameter here is, just because you have low pressure, don't be sure that you have no leakage. Okay, you may have put a huge pump which has just pumped down, and so whatever is coming in, it is able to take out, but constantly some strange molecules are going through the chamber where you are doing processing. That can cause contamination. So watch out on that. Now we can extend that differential equation. So we saw that this was the relationship and we can simply work it out. So for negligible leakage, so supposing these things are very small, as we do in engineering very often, to find the solution we first start off with something which is very simple. So let's assume that there is no leakage. In that case, minus V dP is equal to dt sp. So we can write it down and it becomes first order differential equation. So P becomes P naught, that is the initial pressure, e to the power minus s by V times T plus P ultimate. This comes from the boundary condition, right? P ultimate is at T equal to infinity, what will happen? So this is what it is. Now what is interesting is you get a quantity which is a useful practical quantity, which is V divided by S. V divided by S is the time, right? Because T divided by tau you can put. So tau is equal to V divided by S. And V divided by S you can replace by V times P divided by Q. Okay, this is a useful number. This is called the residual time. So on an average, a molecule that comes into the chamber or present in the chamber is existing in the chamber for that much time. That's what it tells you, given that you are pumping with a pumping speed of S. So that is the key part, that is a useful part here. And but that doesn't mean all molecules are removed. It's an average number. Okay? There are lots of molecules that may linger around for a very long time. Some molecules they come in and immediately get pumped out. That's all there. But on an average, that is the time a gas lingers in that region. This is a useful number, especially when you are doing chemical vapor deposition or something. You are flowing some gases. You want to make sure that it stays long enough so that the reaction takes place. So in such situations, you may want to play with these. And of course, the final ultimate pressure, as we have already seen, is summation of all the parasitic molecules that are coming in divided by the pumping speed. Now, if you plot it, the ideal one, when you ignored this, it will become a straight line. And for high pressures, it is true, because high pressures, most of the molecules that are going out are molecules that are there in the chamber already and nothing that is coming out. Those will be there but very small. So it follows this. So P versus T in log scale is a classic Arrhenius relationship. It will go like that. But in reality, when you go to low pressures, instead of keeping on going low, in theory you can keep on pumping to any low pressure, but in reality it won't happen, because there will always be some leakage path will come, and that will end up limiting what the final ultimate pressure is. So this is the ideal one. Without these when these are present at the low pressure end, they limit what is happening. So you will find an actual curve of the pressure versus time as you are pumping in a chamber be following like this. Initially it will be very nice Arrhenius because your leakages are very small, but with time it starts flattening out to the ultimate pressure that you can get. Okay, so these are practical ways in which you can design a system and understand what is happening. So that being said, now I am not going to go into very much detail, as this is a very basic course. My idea is to just introduce you to something that you can get started, but I just wanted to alert you to the fact that when you are dealing with gas flows, you have to make sure you know what is the regime in which you are using that and what is the model that you are using. So there are three regimes fluid mechanics experts will tell you. Molecular flow, where lambda, the mean free path, is much larger than the characteristic length. Okay, they define a number, Knudsen number, and that is lambda divided by d. K is silent usually, Knudsen number. So lambda divided by d. So where d is the characteristic length. What is the characteristic length? A typical length that will describe a system. Maybe if you have a cube, maybe the diameter is what is describing the chamber. If you have a cubical system, maybe each side or the diagonal, that could be an example of a characteristic length. So this is for Knudsen number, much larger than 1, where what it means is you have no interaction, because lambda is much larger than d. So no interaction between molecules except with the walls of the chamber. Okay, so this is one regime. The other regime is viscous flow, where it doesn't interact with the walls at all. Actually, they interact with each other, and they are actually so laminar flow. These are things where you don't find that they are interacting with the wall, but they are actually going along And so sometimes you need this, sometimes you need that. Okay, sometimes you don't want the wall to interact and the reaction to take place, you may go for viscous flow, and sometimes you need that. In the practical world, of course, you always have an intermediate between the two, and and you have to model each of these, bringing those assumptions. Otherwise it becomes hairy, it becomes too complicated. Of course, with modern computers you can model a lot of these more accurately, even without worrying too much about this from first principles, but that's very computer intensive. Very often it's easier to do some rule of thumb calculation for a system that you're working with, and then you go for further analysis. So you can, depending on what regime you are working, you can actually model this. And similarly, how to define the conductance of various joints, two chambers, how when you connect them, what happens, these are some practical problems you deal with. So you actually have to model these in very careful, elaborate detail. With this, we come to the conclusion of this discussion. I have given you a broad level. Of course, you can always go deeper. So let's see what we have discussed today. The number of molecules present can be estimated by gas laws. This is a useful thing because we need to know what is going into our chamber, what the reactions take place, what remains, are we able to take them out. These are things that we need to know, and these can be found out using gas laws. One can model and understand the possibility of collisions of molecule, and this is a wonderful example of how science helps us understand what is happening. And it's important when carrying out device processing in vacuum systems, because you want to make sure nothing is interacting, and at the various levels of vacuums you chose or you choose to work with depends on how much of interaction you want between the molecules. Now, you can actually model an isothermal system, and most systems you start off assuming isothermal. Of course, if it is not, you'll have to bring in the non-idealities. So for an isothermal system, the throughput Q is equal to SP. This is a very important relationship. S is the pumping speed, P is the pressure, Q is the throughput. Number of molecules per second, S is the volume per second, P is the pressure. Throughput Q is the number of molecules removed per unit time, S is the pumping speed, and P is the pressure. The rate of pumping of a chamber, actually if you go through the elaborate analysis which we did, you find that first order differential equation gives you P is equal to P naught e to the power minus S by V times T plus PU. In this there are two parameters that are useful. V by S would end up giving you what is the residual time, and P ultimate will tell you what is the level of contamination that is there in your chamber. These are things that will give you an idea of what is. So when you are doing processing, you may want to work, if contamination is an issue, you may want to ensure that the pressure doesn't change over time. Then you know at least what the contamination level that you have. If you find that you cannot tolerate it, you have to work to lower that P ultimate. So that is how it will work. Okay. The reference book, actually I would encourage you to read any good textbook that is there on vacuum system. You can also get all the basics in the same reference that we had for the previous discussion. Wolfentauber's chapter 3 that does discuss a lot of them, and he's done a wonderful job in presenting what is actually needed for a process engineer. Okay, so thank you.